Welcome everyone. Today we begin an exciting 62-day journey into the world of low-level design. Over the coming weeks, we are going to transform the way we think about software. We will shift from writing code instinctively to designing systems intentionally. Our goal is simple yet powerful. Think like system architects, build like engineers, and create software that scales beautifully. This course is not just about patterns or diagrams, it is about developing a structured engineering mindset. So let us commit to learning deeply, applying every concept, and growing into confident system designers together. Today we start with the foundation, understanding what low level design really is and why it matters. We will explore the meaning and purpose of LLD, the difference between HLD and LLD, why LLD plays such a critical role in real-world software, key design principles we will follow throughout the course, the mindset of a true system designer, tools and methods we will use, and finally a small hands-on exercise and our assignment. By the end of today, we will have built the mental model that will guide us for the next 62 days. Low-level design is where ideas transform into structure. It bridges the gap between requirements and working code. When we do LLD, we break a feature into logical components, identify classes, objects, and their responsibilities, define attributes, methods, and flows, establish communication between components, apply OOP, solid, and design patterns. Think of LLD as an architectural blueprint at the code level. For example, in an e-commerce system, instead of saying we need checkout, we identify cart, product, user, payment, inventory, and design how they interact before we write any code. This level of clarity makes development faster, cleaner, and more scalable. In software design, there are two key stages, high level design and low level design. High level design is a macro view. We discuss overall architecture, services, databases, and external systems. Low level design is micro view. We define classes, methods, interactions, data flow, and internal logic. HLD decides what the system is made of. LLD explains how each part will work and collaborate. Strong engineers don't just understand code, they understand structure, and LLD builds that structural thinking. Low level design is essential because it creates scalable systems that handle future growth, maintainable code bases that last years, logical and modular software structure, efficient communication with architects and PMs, confidence in interviews and real world projects. Most top tech companies evaluate LLD because it reflects real engineering maturity. When we master LLD, we reduce bugs, speed up development, and build software that stands the test of time. When we write code without design, we are gambling. When we design first, we are engineering. Low level design is not a theory, it runs the world. Every major platform relies on it. Digital payments like UPI and PayPal, food delivery platforms like Zomato, ride sharing systems like Uber and Ola, banking and financial systems, e commerce and booking platforms. Whenever there are connected features, business rules, user flows, or state changes, LLD is involved. Understanding LLD means we can model real world systems reliably. A strong design has key characteristics: modular. Each piece handles one purpose, readable, clear and easy to understand, extensible, easy to add new features, low coupled and high cohesive. Components only do what they should, pattern oriented, uses proven solutions, testable, easy to validate and debug, maintainable, can be improved without breaking things. The golden rule: clarity is more valuable than cleverness. We build systems so that future developers can understand, extend, and trust our work. Before we open an IDE, we think, we analyze requirements, structure concepts, and visualize object interactions. We ask, what are the core entities? What behaviors do they have? How will they interact? Will this design scale? Can this evolve later? Systems are not born inside code editors. They are conceived in our mind first. This mindset separates programmers from engineers. Throughout this course, we will master OOP pillars, the building blocks, solid principles, the foundation of scalability, design patterns, advanced engineering techniques, UML diagrams, visual modeling, clean and clean code and refactoring, professional coding standards, unit testing, ensuring correctness and reliability. We will work with industry tools like Draw.io, Miro, Lucidchart, and VS Code. By the end, we won't just understand LLD, we'll think in LLD. Let's think through a real-world design challenge. We want a coffee machine that can prepare different beverages. Ask yourself, what are the main components? What objects exist? What is each responsible for? Possible classes include coffee machine, beverage, water tank, inventory, user interface. This simple exercise sharpens our breakdown and modeling skills, a habit we will build every day. Now it's our turn to apply today's learning. We will answer what is low-level design, how does HLD differ from LLD, 5 real-world systems that use LLD, UML diagram for a pen notebook system. We can submit it as images, PDF or Google Doc. This is not homework, this is practice to build our system design muscles. Before we wrap up today, let's pause. What changed in our thinking today? Did we notice that software isn't just code? It's structure, thought, organization, clarity. Reflection anchors learning. We don't want to just attend a session, we want to transform our thinking. Tomorrow we strengthen our OOP fundamentals, encapsulation, inheritance, polymorphism, and abstraction. These aren't just theory terms, they are the backbone of every scalable system. Let's come prepared with our laptops, notebooks, and UML tools because tomorrow we move a level deeper into engineering excellence. This journey is long, but every day will build our mindset, our skills, and our confidence. We are not just learning LLD, we are learning to think like world-class engineers. Today we planted the seeds of design thinking. Systems are conceived in our minds, structured through diagrams, defined by principles, and only then written as code. Tomorrow we build the foundation that powers all great systems, strong OOP design. Let's continue forward with curiosity, discipline, and excitement. Welcome to day 2 of our 62-day low-level design mastery course. Today we are diving into one of the most important foundations of software design, object-oriented programming or OOP. This session will set a strong base for all the design work we will do in this course. In this session, we will refresh our core understanding of object-oriented programming. We will walk through the 4 pillars of OOP, see real-world examples, compare key concepts, and practice small exercises. By the end, we will be ready to apply OOP effectively in real LLD problems. OOP or object-oriented programming organizes software into objects and classes. It helps us model real-world entities in a structured and meaningful way. With OOP, our systems become modular, easier to maintain, easier to extend, and more aligned with real-world logic. OOP stands on 4 foundational pillars: encapsulation, inheritance, polymorphism, and abstraction. Each plays a key role in creating flexible, scalable, and maintainable systems. Encapsulation means binding data and behavior inside a single unit, typically a class, and protecting internal details. This helps us keep our data safe, enforce rules, and ensure controlled access. For example, in a banking system, we don't expose account balances directly. We update them through methods. Inheritance allows one class to acquire the properties and behavior of another. It supports code reuse and helps us build logical hierarchies. For instance, a user class can be extended into admin and customer classes. However, we must be careful. Deep inheritance can make systems rigid, so we always consider composition first. Polymorphism means one action behaving differently depending on context. We see this through method overloading at compile time and method overriding at runtime. In a payment system, the method like pay can behave differently for UPI, card, or wallet payments. Abstraction is about focusing on what something does instead of how it does it. We hide implementation details and expose only necessary functionality. Interfaces and abstract classes are used to achieve abstraction. For example, a payment interface can have multiple implementations. Both abstract classes and interfaces help with abstraction, but they serve different purposes. Abstract classes allow partial implementation and are suited for closely related classes. Interfaces define capabilities and allow multiple inheritance, ideal when different classes must support the same behavior. A very important principle in modern OOP design is prefer composition over inheritance. Instead of forcing deep classes hierarchies, we build systems where objects collaborate. A car has an engine, that is composition. A car is a vehicle, that is inheritance. As we design classes, we must aim for high cohesion, that is each class having one focused responsibility, and low coupling, which is minimal dependency between components. We avoid God classes, we encapsulate what varies, and we always keep maintainability in mind. Let's look at a familiar real-world example, the Uber ecosystem. We have users like riders and drivers, a ride entity, locations, and multiple payment methods. This structure maps naturally into classes and relationships, showing how OOP aligns with real systems. As a quick practice, we will design an online course system. We identify key entities such as course, student, and instructor, and define relationships and behaviors. This helps us strengthen our object-oriented thinking. These are common interview questions around OOP. Understanding the difference between abstraction and encapsulation, method overloading versus overriding, and composition versus inheritance will help us excel in LLD interviews. Our homework today is to model a library system OOP design. We will define classes, create UML diagrams, and demonstrate all four pillars. This assignment prepares us for real system challenges. To summarize, encapsulation helps us protect and bundle data. Inheritance supports hierarchy and reuse. Polymorphism enables flexible behavior, and abstraction helps us hide complexity. Together, these principles form the backbone of good object-oriented design. In the next session, we will move into solid principles, the foundation of scalable and professional low-level design. These principles combined with OOP will elevate our design skills to an industry-ready level. Welcome back to day 3 of our 62-day low-level design course. Today we will explore one of the most foundational and transformative concepts in object-oriented programming, the solid principles. Whether you are designing a small module or a large-scale application, these principles guide us in building software that is clean, adaptable, and future-proof. Our goal for this session is to demystify solid, illustrate how each principle works in practice, and equip you with the mindset to apply them in your everyday coding decisions. Have you ever worked on a code base where changing a single line of code breaks 10 unrelated things, or struggled to add a new feature without rewriting the half module? These problems are often the result of poor design. Solid principles introduced by Robert C. Martin, affectionately known as Uncle Bob, are the antidote. They help us write software that is easy to maintain, extend, and test. In other words, they reduce the cost of change, a key goal in software design. Today, we will see how Solid can turn messy code into a joy to work with. So, what exactly is Solid? It's an acronym for five design principles that, when followed, result in robust, modular, object oriented code. The five principles are single responsibility, open closed, scope substitution, interface segregation, dependency inversion. Each principle addresses a specific pain point in software design, from managing class responsibilities to dealing with tight coupling. They may sound abstract at first, but by the end of today, you will see how practical and powerful they really are. Let's begin with the S in solid, the single responsibility principle or SRP. The idea is simple. A class should do one thing and only one. That means it should have only one reason to change. For example, consider a user manager class that handles user authentication, data access, and login. If you change the way you authenticate users, you risk affecting logging. That's too many responsibilities under one roof. By separating concerns into auth service, user repository, and logger, we reduce risk and increase modularity. SRP makes your class focused, easier to test, and easier to reason about. Think of it like the difference between a Swiss Army knife and a precision tool, both useful but for very different purposes. Next, we move to the open closed principle. This one says that software entities that are classes, modules, functions should open for extension but closed for modification. That means we should be able to add new features without rewriting existing code. Imagine a payment processor class that supports credit card payments. Now we want to support UPI or PayPal. Instead of modifying the existing logic, which risks breaking it, we introduce a common iPayment method interface and implement new payment types as separate classes. This keeps the original code intact and promotes reusability. The open-closed principle shields stable code from frequent change, which is especially useful in large or legacy systems. The least-scope substitution principle or LSP builds on inheritance. It says that any subclass should be substitutable for its base class without altering the correctness of the program. That sounds technical, but here's a relatable example. Let's say you have a bird class with a fly method and you create a penguin subclass. Penguins don't fly. If the program expects every bird to fly and you insert a penguin, things break. That's a violation of LSP. To fix it, you might rethink your hierarchy or separate flying behavior into its own interface. LSP helps us avoid misusing inheritance and encourages better abstraction. Now let's talk about interface segregation. This principle says don't make clients implement interfaces they don't use. It's about avoiding fat interfaces. Picture this. You have an iMachine interface with methods like print, scan, and fax. But what if you are building a basic printer that only prints? Should it be forced to implement all those methods? Absolutely not. The solution is to break the large interface into smaller ones: iPrinter, iScanner, and iFax. Each client now depends only on what it actually uses. Interface segregation promotes flexibility and reduces unnecessary dependencies, which makes our system more adaptable. Finally, we arrive at the dependency inversion principle, one of the most powerful and misunderstood principles. It states that high-level modules should not depend on low-level modules. Instead, both should depend on abstraction. Let me explain. If your application service depends directly on file logger, then any change to how logging works means changing the service too. But if both depend on a iLogger interface, you can swap in file logger, console logger, or even a database logger without touching your core logic. This principle encourages you to code to interfaces, not implementations. It also opens the door to dependency injection, a technique we will cover later, which leads to highly decoupled testable code. Let's see the difference solid makes. On the left, we have a before scenario, a monolithic class doing everything from business logic to persistence to formatting. It's hard to test, hard to maintain, and prone to errors. On the right side, we see the same system refactored with solid principles. Responsibilities are clearly separated, classes are loosely coupled, and changes in one area don't repel through the rest of the system. It's more scalable, readable, and elegant. This is what Solid enables. Let's take a short quiz to reinforce what we have learned. You will see multiple choice questions and code snippets. Your job is to identify which solid principle is being violated or applied correctly. Feel free to discuss your reasoning with a partner or in small groups. The goal here is not just to memorize definitions, but to train your design instinct to start spotting design flaws the way experienced developers do. Let's reflect for a moment. Which solid principle felt most natural to you? Which one challenged your current coding habits? Can you think of a time you accidentally broke one of these principles? Maybe by stuffing too much into a class or tightly coupling your service to a database. These are great points for discussion. By sharing your thoughts and hearing others' perspectives, you deepen your understanding and start to internalize these principles. Your assignment is to review and refactor a sample food delivery module that violates multiple solid principles. You will analyze the design, identify the violations, and rework the classes to align with what we have learned today. Be thoughtful. Think about abstraction, dependency management, and responsibility separation. Submit your work by day 5 and of day. We will do a peer review on day 6 to compare solutions and discuss different design approaches. If you want to explore more, I recommend Agile Software Development by Robert C. Martin. It's a foundational read for design principles. Also check out refactoring.guru, an amazing resource with visual guides and interactive examples. I have shared a downloadable cheat sheet and optional video lectures to help reinforce today's material. Design mastery doesn't come from a single day. It comes from repeated exposure and practice. To sum up, SOLID is more than just an acronym, it's a mindset. These five principles give us the tool to write code that lasts, evolves, and scales. As we move forward in these codes and in our career, that these principles guide our design thinking. Don't just write code that works, write code that works well and works long. Practice, refactor, and refine. That's the essence of great software design. Thank you for your attention. Hello and welcome to day 4 of our low-level design course. Today we embark on an essential journey, one that introduces us to a developer's toolbox of timeless solutions, design patterns. These are not just academic concepts, they are living, breathing techniques used daily by engineers at companies like Google, Amazon, and Netflix. Whether you are building a small CLI app or architecting a large scale system, design patterns provide a structured way to solve problems elegantly and efficiently. Let's dive in. Before we go any further, we need to answer the fundamental question: what exactly are design patterns? Simply put, they are proven solutions to recurring design problems, templates that help us structure code in a clean, reusable way. They are not lines of code you can copy paste, they are conceptual building blocks. Design patterns were popularized by the Gang of Four, a group of software engineers who documented these patterns in a landmark book back in 1994. The goal: to empower developers with strategies that have stood the test of time. Once you learn to spot these patterns, you will start seeing them everywhere in libraries, frameworks, and open source tools. You might be wondering, why do I need patterns if I can just write custom logic? Good question. Design patterns bring standardization and predictability. They reduce the time you spend reinventing the wheel. They help prevent bugs by offering tried and tested approaches. They also enable better collaboration. When you say, let's use the strategy pattern, your teammate knows exactly what you mean. No need to explain from scratch. In a nutshell, patterns are like shared wisdom. They make your designs smarter, your code cleaner, and your team stronger. Design patterns are broadly classified into three categories. First, creational patterns, which deal with object instantiation. They help decouple the creation logic from usage, giving you more control and flexibility. Second, structural patterns. These are about composition, how different parts of your code relate and work together. They improve maintainability by structuring code in neat, scalable ways. And finally, behavioral patterns. These are all about communication. How does one object interact with another? Who knows what and when? Together, these categories cover the core concerns of software design: creating, connecting, and communicating. Creational patterns focus on how objects are created. Instead of calling constructors everywhere, we use patterns that control object creation logic, which can help us enforce consistency, flexibility, or performance. Examples include the singleton, which ensures a class has only one instance, useful for things like configuration or logging. The factory method, which creates objects without exposing instantiation logic to the client. The builder pattern, which lets us construct complex objects step by step. Use creational patterns when object construction is complex or when you want to abstract away dependencies. Structural patterns are like architectural blueprints. They help you compose classes and objects to form larger structures, all without losing flexibility. For example, adapter helps you connect incompatible interfaces like plugging a USB into an HDMI port. Decorator lets you dynamically add behavior to an object. Think of it like dressing up your coffee with milk, sugar, or caramel. Facade provides a simplified interface to a more complex system, just like how your TV remote hides the internal circuitry. If your system is becoming messy or too tightly coupled, structural patterns can clear things up. Behavioral patterns focus on how objects communicate and behave. They help distribute responsibility in a flexible and dynamic way, a key to achieving low coupling and high cohesion. Some examples include strategy, which lets you define a family of algorithms and switch between them at runtime, like choosing between different sorting methods. Observer, where objects subscribe to events and react when changes happen, perfect for event-driven systems. Command, which turns requests into standalone objects, enabling undo, redo, and queuing. Behavioral patterns make your code more adaptive to change and easier to maintain. Let's take a moment to connect these patterns to the real world. Design patterns can sound abstract at first, but they are everywhere around us. For instance, a singleton is like your system's configuration manager. There's only one and it's shared globally. A factory is like a restaurant kitchen. You place an order and the kitchen prepares it based on input. You don't care how it's done. A decorator, think of it as customizing your drink. Base coffee plus add-ons like milk, cream, and flavor shots. And the observer pattern is like YouTube subscriptions. You get notified when your favorite creator uploads a new video. Using analogies helps us internalize these abstract ideas more naturally. Now let's talk about when to use patterns. Patterns shine when you recognize a recurring structural or behavioral problem. They are also helpful when you want your code to be extensible, when you anticipate future change. But be aware, patterns aren't silver bullets. Avoid over engineering. Don't use patterns just to sound smart in code reviews. Sometimes a simple class does the job better than a complex pattern. Speaking of caution, let's touch on anti-patterns. These are common traps developers fall into when misusing patterns or ignoring good design. The God object, for example, is a class that tries to do everything, leading to bloated, unreadable code. Spaghetti code refers to unstructured logic that's tensed and hard to maintain. And overusing singleton can make your code rigid and hard to test. The key takeaways: use design patterns mindfully. They are tools, not trophies. Let's make this hands on. You will be presented with short, real world scenarios and asked to choose the most appropriate patterns. For instance, if you want to allow user to switch payment methods at runtime, you are looking at the strategy pattern. If you want a single configuration instance for your app, that's singleton. If you want to add logging without touching existing code, think decorator. These exercises help you build your instinct for recognizing patterns in the wild. To go further with design patterns, use tools that support visual thinking. Lucidchart and Draw.io are great for diagramming class structures and flows. Code editors like VS Code or IntelliJ help you implement and refactor patterns with ease. I also recommend two resources: the Design Patterns book by the Gang of Four, a must read, refactoring.guru, an amazing interactive site that visually explains each pattern in multiple languages. Now it's your turn to practice. Pick two creational patterns, say singleton and factory, and implement them in your preferred language. Try to relate them to a real world problem. Also browse through an open source repository and see if you can spot any patterns. As a bonus, draw UML class diagrams of your implementations. This will help solidify your understanding. Let's wrap up. Today we learned that design patterns are not about complexity, they are about clarity. They give us a vocabulary to reason about design, solve common challenges, and write cleaner, more maintainable code. Remember the three code types: creational, how to create objects; structural, how to relate objects; behavioral, how objects communicate. The more you practice, the more natural patterns will feel. So keep coding, keep designing, and soon you will think in patterns. Welcome to day 5 of our low level design course. Over the past few days, we have been laying a solid foundation for designing clean, modular, and scalable software. Today, we will dive into an essential toolset used by software engineers around the world: UML diagrams. Unified modeling language helps us visualize the building blocks of our systems. Whether it's the way different classes interact or how a user flows through a process, UML gives us a shared visual language to reason about our systems more clearly. So let's get into it. In today's session, we have four major goals. First, we will understand why UML plays a critical role in low-level design and how it fits into the bigger picture of system design. Second, we will explore four commonly used UML diagrams: class, sequence, activity, and component diagrams, each with its own use cases and purpose. Third, we will learn some practical tips for creating effective and clean diagrams that communicate well. And finally, we will get to apply what we have learned with hands-on exercises and tasks that simulate real-world design situations. So what exactly is UML? The Unified Modeling Language is a standardized way to describe and document the structure and behavior of a software system. It's like a blueprint that helps software engineers, architects, testers, and even business analysts get on the same page. Originally developed to consolidate different modeling methods into one standard, UML has become the go-to modeling language in software development. It allows us to think visually, turning abstract requirements and code structures into concrete, communicable diagrams. Using UML in our low-level design process provides several key benefits. First, it makes the relationships between components crystal clear. We can easily spot tight coupling, duplication, or missing abstractions. Second, UML diagrams help uncover flows early in the development process before any code is written, which saves time and cost. And third, they foster better communication across your team and improve maintainability by documenting the system visually for future developers to understand. Let's start with class diagrams, which are perhaps the most widely used in object-oriented programming. Class diagrams depicts the static structure of our system. They show the classes we will use, their attributes and methods, and how they relate to one another. Common relationships include association, where one class references another, inheritance, where a subclass extends a parent, aggregation, where one class logically contains another, and composition, where the relationship is tighter and more lifecycle bound. Think of a class diagram as a snapshot of your system's data model. To design effective class diagrams, focus on clarity and simplicity. Start by ensuring each class has a single responsibility. Don't overload a class with too many duties. Use meaningful names for classes and attributes so they are self-explanatory. Finally, avoid clutter, group related classes logically, and remove unnecessary details. A clean, focused diagram is more valuable than an overly complex code. Let's put this into practice. Our task is to create a class diagram for a student course enrollment system. Start by identifying the key entities student, course, and enrollment. Ask yourself what attributes and methods should each class have, how they relate. For example, a student can enroll in multiple courses, and a course can have multiple students, which makes enrollment a linking entity. Try sketching this relationship and include attributes like student name, course title, and enrollment date. Now let's talk about sequence diagrams. These diagrams illustrate how objects interact with one another in a specific scenario over time. Each object has a lifeline and messages are represented as arrows. This is useful when you want to capture a flow of operations like how a user logs in or books a ticket. The vertical axis represents time and horizontal axis shows the objects participating in the process. You will also see activation bars which represent periods where an object is active or executing logic. To make your sequence diagrams clear and useful, focus on a single scenario part diagram. Don't try to capture every possible branch or exception. Keep it simple. Align your objects evenly and use arrowheads properly to indicate call direction. And if possible, annotate messages with details like method names or parameters to make them self-explanatory. Here's a practical exercise. Create a sequence diagram for a password reset flow. Start with the user who initiates the process by submitting their email. The auth service validates the email and calls the email service to send a reset link. Show this sequence of interactions and try to capture the timing and dependencies between each message. This is a common scenario in many systems and is a great way to practice sequencing. Activity diagrams are great for modeling workflows, especially those that involve decisions, loops, or parallel actions. They are similar to flowcharts but more structured and suited for software modeling. You can use them to show the logic of business processes, user flows, or algorithmic steps. Key elements include activities, decisions, merge points, and synchronization bars. They help clarify what happens next logic in a system. Let's try creating an activity diagram for a food delivery app. The workflow might begin with the user browsing the menu, adding items to the cart, and placing an order. The system processes the payment, confirms the order, and starts preparing it. Think about the decision points such as payment success or failure, and parallel tasks like updating inventory and notifying the kitchen. Map it all visually using activities, decisions, and flow connectors. Component diagrams gives us a higher level view of our system's architecture. They show how different modules or services are packed and how they interact through interfaces. This is especially useful when working with microservices, layered architectures, or large-scale enterprise systems. Think of components as black boxes that encapsulate specific functionality, each with its own responsibilities, interfaces, and dependencies. Let's apply component diagrams to a cab booking system. We are likely have rider service for users, driver service for drivers, trip service for managing trips, and payment service for handling payments. Draw each of these as separate components and indicate how they connect and communicate, for example through REST APIs or messaging queues. This helps clarify responsibilities and integration points across the system. There are plenty of great tools to help you create UML diagrams. Lucidchart and Draw.io are excellent for quick drag and drop diagramming. StarUML is a more robust tool that supports detailed modeling and exporting. If you prefer something code-based, try PlantUML. It lets you write diagram definitions in plain text and auto-generates visuals. Choose a tool that fits your style and project needs. Now it's your turn to bring everything together. Design a library management system using UML diagrams. Start with a class diagram to show entities like book, member, and loan. Then draw a sequence diagram showing the flow when a book is issued. If you are up for it, go further and model an activity diagram for the return process and a component diagram to show modularity. This task reinforces everything what we have learned so far. Let's recap. UML is a visual language that bridges the gap between abstract ideas and working software. Today we explored the different UML diagrams, understood their roles in LLD, and practiced using them for real-world systems. Remember, diagrams are not just for documentation. They are thinking tools that help us design better, communicate faster, and avoid costly mistakes. Before we wrap up, here's a thought. Have you ever worked on a project where a simple misunderstanding caused delays or rework? Now imagine if you had a diagram to align everyone's understanding early on. UML is more than just lines and boxes. It's about clarity, alignment, and reducing friction. Feel free to share your thoughts on or stories in the group discussion. Thank you for your attention. Welcome to day 6 of our 62-day low-level design course. Today marks a pivotal point in our design journey as we begin building the real structural backbone of any object-oriented system, classes and interfaces. Designing them well is not just about syntax, it's about clarity, responsibility, and long-term maintainability. Whether you are working on a small utility or a complex enterprise system, strong class and interface design is what transforms good code into great architecture. Let's get started. Before we dive in, here's what we will take away from today's session. First, we will learn the core characteristics of a well-designed class, what to aim for and what to avoid. Second, we will explore how interfaces provide abstraction, allowing for flexibility, reusability, and testable code. Third, we will revisit the single responsibility principle or SRP and see how it keeps classes focused and easier to maintain. And finally, we will look at class relationships, how objects interact, depend, or extend one another. By the end, you will be equipped to design your own modules that are not only correct but clean and scalable. Let's start with the basic question: what exactly makes a good class? A good class encapsulates both data and behavior in a logical, self contained unit. It should not just hold state but also define how that state changes. It should have high cohesion, meaning it should only do one logical job. This makes it easier to understand and modify. It should also have low coupling, meaning it does not depend heavily on the internal workings of other classes. The less your class knows about others, the easier it is to change, reuse, and test in isolation. Think of each class as a self-reliant, single-purpose machine. It does its job and communicates cleanly with others through well-defined interfaces. The single responsibility principle is a cornerstone of good design. It states that a class should have only one reason to change. That means each class should focus on one responsibility or concern. If your task manager class is also logging errors, sending notifications, and updating databases, it's doing too much. Instead, you should break those responsibilities into focused units. Have a logger, a notifier, and maybe a repository. This separation makes your code easier to test, extend, and debug. Classes with multiple responsibilities become harder to maintain over time because changes in one feature can accidentally break another. SRP helps us guard against that risk. Now let's differentiate between interfaces and classes. An interface defines what needs to be done, while a class defines how it's done. This distinction is powerful. By programming to an interface, not a concrete class, you gain the flexibility to switch implementations without changing client code. For example, a payment processor interface can have different classes like credit card processor, PayPal processor, or UPI processor. This also supports dependency inversion, one of the solid principles, which states that high-level modules should not depend on low-level modules, but both should depend on abstraction. Interfaces make your system extensible, modular, and test-friendly. Classes don't live in isolation, they interact, and understanding how they relate to one another is key. Association is a general connection one class uses another. Aggregation is a has a relationship, but both objects can exist independently. For example, a university has students, but students can exist without the university. Composition is stronger. If one object is destroyed, the composed objects are two. Think of a house composed of rooms. Remove the house, and the rooms no longer make sense. Inheritance, on the other hand, creates an easy relationship. A dog is an animal. It allows for polymorphism but should be used carefully to avoid tight coupling. Knowing when to use each relationship helps you architect clean, expressive systems. Designing interfaces well is more of an art than a science. Always try to keep your interfaces focused and minimal. The interface segregation principle reminds us that no client should be forced to depend on methods it does not use. If your interface is becoming too large, break it down. Also favor extension, add new interfaces over modification, which can break client code. Use interfaces to decouple your business logic from the actual implementation. It will make your code much easier to mock and test. And finally, avoid creating God interfaces that try to do everything. They are hard to implement and hard to maintain and violate several design principles at once. Let's look at a code example to reinforce what we have discussed. Here we have an assignable interface with a single method assigned to. Then we have a task class implementing that interface. The task class holds a private user and provides its own implementation of assigned to. This design is elegant and scalable. Today, if we introduce a bug, event, or reminder, all of them can implement the assignable interface, each in their own way. This is how we build systems that are extensible without changing existing code. Now it's your turn to apply what we have learned. Your task is to design a simple task management system. Define classes like task, user, project, and status. Think about what behaviors can be abstracted into interfaces, maybe assignable, trackable, or prioritizable. Create a UML diagram first to visualize your design and then bring it to life in code. Don't worry about making it perfect. Focus on clarity, separation of concern, and applying SRP. For today's assignment, you will design an online quiz platform. Identify the key entities like question, quiz, user, submission, and so on. Think about which classes should interact, which behaviors belong in interfaces, and how to apply SRP. Your submission should include a UML class diagram and a short write-up around 300 words explaining your design choices. This is your opportunity to showcase your understanding of modular class design, abstraction, and system organization. Welcome to day 7 of our low-level design course. Today we dive into one of the most essential but often overlooked areas of software design: error handling and exception management. When systems grow in complexity, so does the number of things that can go wrong. From user input errors to third-party service failures and internal bugs, exceptions are inevitable. But with proper design strategies, we can ensure our applications fail gracefully, remain maintainable, and deliver a reliable experience to users. Let's explore how to design error handling flows that are both thoughtful and robust. Why do we focus so much on error handling? The answer is simple. Failures are a given in any real world system. Whether it's a null pointer, a network call that times out, or a user submitting invalid data, systems must be able to handle these gracefully. Good error handling allows for quick diagnosis and recovery. It supports testability by exposing clear paths of failure, and most importantly, it enhances user experience by providing meaningful feedback rather than cryptic code errors or application crashes. So, error handling isn't just defensive programming, it's a cornerstone of thoughtful software design. Errors can generally be divided into three types. First, we have compile time errors. These are caught during development, like syntax mistakes or missing method implementations, and are relatively easy to fix because they are flagged by the compiler. Next, we encounter runtime errors. These slip past the compiler and emerge only when the program runs. For example, accessing a null object or dividing by zero. Lastly, there are logical errors. These are the most dangerous because your code runs without crashing, but it produces incorrect results, perhaps due to a flawed algorithm or incorrect assumption. As designers, it's crucial we understand these types so we can build systems that detect, isolate, and recover from them effectively. In many statically typed languages like Java, exceptions are categorized as either checked or unchecked. Checked exceptions must be explicitly declared and handled. These represent recoverable situations like a missing file or a failed database connection. You can anticipate them and design fallback behavior. Unchecked exceptions, on the other hand, indicate bugs in the program, such as null pointer dereference or an illegal argument. These are typically caused by programming errors, and while you might catch them, it's often better to fix the root cause. This classification helps us distinguish between predictable system failures and unintentional code defects. Let's look at some proven best practices in designing exception flows. First, fail fast. If something is wrong, don't delay detection. Raise errors early and clearly. Second, never swallow exceptions silently. Always log them with enough context so developers can debug easily. Third, use custom exceptions to represent business level errors. They provide clarity and intent. Avoid generic catch all blocks unless you are at a very high level, like an error boundary. And finally, always log with relevant context such as input, user session, or timestamp. These practices improve observability, simplify debugging, and lead to better system behavior over time. Where you handle exceptions in your system matters a lot. Should the service layer handle them or should the controller? A good pattern is to let lower layers throw exceptions upward and handle them centrally in a top level layer like a controller or global middleware. This avoids cluttering your business logic with try-catch blocks. In microservices, centralized handlers ensure consistent error responses. Also design retry logic wisely, especially when calling external services, and always have fallback mechanism in place, like showing cached data if live data isn't available. These patterns ensure systems degrade gracefully under pressure. Custom exceptions are powerful tools. Rather than using generic exception classes, define domain-specific ones that explain exactly what went wrong. In this example, product out of stock exception extends runtime exception and clearly states which product ID failed due to being out of stock. This makes your error logs, exception handlers, and business rules more expressive. It also encourages developers to think in terms of the domain, not just technical failures. Well-named exceptions act like documentation. They explain your design decisions without comments. In real-world systems, centralizing your exception handling is a huge win. Frameworks like Spring Boot offer tools like REST controller advice to catch exceptions across your entire application. In this snippet, we define a global handler for our product out of stock exception. We return a clear HTTP status and a message, ensuring clients receive consistent responses. Centralization also makes it easier to implement features like logging, notifications, or altering. By separating exception handling from business logic, we keep our code clean, testable, and scalable. Now let's put these ideas into practice. Your task is to build an error handling module for an online shopping cart. Define at least 3 custom exceptions, perhaps for inventory issues, invalid payment methods, or expired discount codes. Handle them in your service layer with clear logging. Implement a centralized exception handler to format your error responses. Bonus, add retry logic for your payment gateway. This exercise brings together everything we have learned today and gives us a real taste of designing for reliability. Let's highlight some common mistakes. First, avoid catching exceptions or throwable unless absolutely necessary. It hides the true cause and makes debugging harder. Second, don't suppress exceptions silently. If an error happens and you don't log or report it, you are setting yourself up for disaster. Third, never use exception to control flow. It's inefficient and confusing. And finally, be mindful of thread level failures in concurrent systems. Just because your main thread is running doesn't mean background tasks are. Always have a strategy for thread exceptions propagation. Let's quickly review what's the difference between checked and unchecked exceptions. Why should you bother creating custom exceptions? And what's the danger in catching all exceptions without discrimination? These questions will help reinforce our understanding. Take a moment to reflect or discuss them with peers. It's a great way to internalize today's material. Before moving on, be sure to complete your deliverables for today. First, implement 3 custom exception classes that represent real business scenarios. Second, draw an exception flow diagram to to visualize where and how errors propagate through your system. And third, write a centralized handler that ties everything together. This will not only help you grasp today's concepts but will also serve as valuable building blocks for your final capstone project. Thank you for your attention. Hello and welcome to day 8 of our low level design course. Today's focus is on something that isn't just important, it's essential. We will be discussing clean code and code readability. Writing code that works is only the beginning. As developers, we aim to write code that is easy to read, easy to understand, and easy to maintain. Clean code is what makes collaboration possible, debugging easier, and scaling sustainable. Throughout today's session, we will explore best practices, naming conventions, formatting, and real world techniques to help us all write professional, grade, maintainable software. Let's start by understanding why code readability matters so much. Think about this. Code is read more often than it is written. You might write a function once, but your teammates, future maintainers, or even you 6 months from now will read it over and over. Readable code reduces the cognitive load needed to understand it, which means fewer bugs, faster onboarding of new team members, and quicker development cycles. Remember, code isn't just for machines. Compilers and interpreters don't care how your code looks. It's people who read your code. So write them. Good code starts with good names. Clear, intentional naming of variables, functions, and classes can make your code self-explanatory. Names should reflect the purpose and intent, not just the type or structure. Avoid vague names like temp or val1. Instead, use names like user profile or transaction amount, names that tell the story. Stick to a consistent naming pattern throughout your code base. Camel case, snake case, prefixing, whatever your team uses, be consistent. Naming is communication and clarity is king. Let's compare some examples. If you see a variable named val1, what does it mean? It forces you to dig deeper, but a name like order total immediately communicates its role. Similarly, a function named doStuff tells you nothing about what it actually does, but saying ML needed notification gives clarity and confidence. Ask yourself, if I read this name in isolation, would I understand its purpose? Functions are the building blocks of our logic, and designing them well makes your code more readable and maintainable. Each function should do one thing and do it well. Avoid writing long, multi-purpose functions. Instead, break them down into smaller ones, each responsible for a single task. Give them names that clearly indicate their job. When a function name is well chosen, comments become almost unnecessary. Also, be cautious of side effects. Your function should behave predictably and not unexpected change the program. Even though formatting might seem superficial, it plays a big role in readability. Clean formatting guides the reader's eye. Use consistent indentation, place related code together, and leave blank lines to separate logical blocks. Avoid crowding the code with too much in one line or one block. Following a team or project style guide ensures uniformity, which makes switching between files or working with teammates much easier. Good formatting is like good grammar, it keeps the message clear. Comments are helpful, but only when used with purpose. You don't need to comment every line or state the obvious. Increment I by 1 is not helpful if the code already says I++. Instead, use comments to explain why something is done, especially if the reason is not obvious. Also, watch for outdated comments. They can mislead and confuse. A good rule of thumb: if you find yourself writing a lot of comments to explain what the code is doing, it might be a sign that the code itself isn't clear enough. Now let's talk about some red flags, things that make code hard to read or maintain. Long methods, huge classes, and deeply nested conditions are often signs of trouble. Magic numbers, that is, hard coded values without context, should be replaced with named constants. Overusing flags, booleans, or writing code that has to check too many conditions often points to poor design. These are all considered code smells. While not outright errors, they are signs that your code could be improved through refactoring. Refactoring is a process of improving your code's structure without changing its behavior. It's something every developer should regularly do. You might break down large functions into smaller ones, extract common logic into helpers, or simply rename a few poorly chosen variables. The key is to make your code cleaner and easier to understand. And remember, refactoring isn't a one time task, it's a continual part of software development. We are not alone in our quest for clean code. There are many tools that can help. Linters like ESLint or CheckStyle catch style issues early. Formatters like Prettier or Black automatically aligns your code to consistent standards. IDEs also offer built-in tools for reformatting and restructuring. Using these tools helps enforce discipline and allows teams to focus on writing logic, not debating space or indentation. Let's summarize everything. Prioritize clear over cleverness. Write code that's simple and expressive, not code that requires decoding. Don't optimize prematurely. First, make it clear, then make it fast. Stay consistent with naming, formatting, and structure. And one of my favorite quotes to remember from Kelsey Heightor: easy to delete is better than easy to write. That's the essence of clean code. Build systems that others can understand and improve. Time to put this into practice. Here's a piece of messy, unclear code. Your task is to refactor it using everything we have learned today. Rename variables, split large functions, clear up formatting. When you are done, explain your choices. This helps develop your judgment and teaches you to see through messy logic to the elegant solution beneath. For homework, take a legacy code snippet of around 100 to 200 lines. Your job is to refactor it completely. Submit the before and after versions and write a short reflecting on what you improved: naming, structure, readability, or design. And if you are up for a challenge, build a small feature from scratch using all the clean code principles we have discussed today. Clean code is a habit, a mindset, and a sign of craftsmanship. It's not just about making things work, it's about making them beautiful and understandable. It helps teams move faster, prevents burnout, and reduces technical debt. As you continue building software, keep readability and elegance in mind. Every line you write is a message to another developer. Make it a kind and thoughtful one. Thank you for your attention. Hello and welcome to day 9 of our low level design course. Today we are going to explore two incredibly important concepts: dependency injection and inversion of control. These ideas are everywhere in modern software systems, whether you are building a tiny app or a massive enterprise system. Once you master them, you will write cleaner, testable, and much more flexible code. Let's dive right in. Alright, let's start with dependency injection, or simply DI. In simple words, DI means that an object does not create its own dependencies. Instead, it gets them from somewhere else. Think of it like hiring a contractor. You don't manufacture the tools they need, you just give them the tools. This idea leads to cleaner design because classes don't need to worry about how to build their dependencies, just use them. Now, dependency injection is just one form of a bigger idea called inversion of control, or IOC. Traditionally, code controls everything. It decides what to instantiate, how to wire things together. But with IOC, we flip that model. We hand over that control often to a framework or an external entity, so the framework decides when and how things are created. Dependency injection is how we implement this inversion by injecting ready-to-use dependencies into our class. You might wonder why bother. Well, when classes directly create their dependencies, they become tightly coupled. That's bad news for testing, flexibility, and long-term maintenance. But with dependency injection, we can swap out implementations easily. For instance, in testing, we can inject a mock instead of a real service. In production, we can inject a different version based on configuration. In short, DI helps us achieve loose coupling, high testability, and future-proof designs. Now, there are three major types of dependency injection we should know. First is constructor injection, where we pass the dependencies at the creating of the object. Second is setter injection, where we set dependencies later via public methods. And third is interface injection, which is less common but still important, where an interface forces an object to provide its own dependencies through specific methods. Each method has its own strengths depending on the situation. Let's look at constructor injection in action. Imagine a car class that needs an engine. Instead of building the engine inside the car class, we pass the engine in when constructing the car. This ensures that the car always has a working engine and we can easily substitute a petrol engine, diesel engine, or even an electric engine depending on the need. Constructor injection is the most preferred method when a dependency is mandatory for the object to function properly. Here's another pattern, setter injection. This time the car has a method like set engine to install an engine after it's constructed. Setter injection gives more flexibility, like configuring optional components later, but it comes with a small risk. The object can exist in a semi-initialized state until all dependencies are set. It's best used for optimal dependencies or where late binding is necessary. Dependency injection isn't just theory, it's everywhere. In the backend framework like Spring Boot, services are automatically injected for us. In frontend frameworks like Angular, components receive their dependencies via injection. In mobile apps like Android development, libraries like Hilt and Dagger manage DI. Even in games, platforms, physics engines, or audio engines are injected depending on the platform. Mastering DI makes us much more comfortable with modern software development. Managing DI manually is fine for small projects, but as projects grow, we need automation. That's where dependency injection containers come into play. These are special libraries or frameworks that automatically resolve dependencies, instantiate objects, and even manage object lifecycles like singleton, scope, or transient. Examples include Spring's IOC container, Juice for Java, Boost.di for C++, and even .NET Core's built-in DI container. Before we run off and apply DI everywhere, beware of some common pitfalls. First, don't inject too many things into one class. If you have 5 or 6 dependencies, maybe we need to rethink our design. Second, don't make all dependencies optional. That leads to fragile objects. Third, don't over-engineer small projects by building complex DI setups. It's important to match the complexity of the solution to the size of the project. Now it's your turn to apply these ideas. Try implementing a payment service that depends on a payment gateway. Pass the gateway using constructor injection. Then take an old piece of code you have written earlier and refactor it to use DI instead of direct instantiation. As a challenge, you can even build a tiny DI container. Trust me, it's a great exercise to truly understand how dependency resolution works. Alright, to summarize everything we learned today, Dependency injection allows our code to be loosely coupled and easily testable. Inversion of control is a larger principle at work, and DI is one of the most effective implementations. Constructor injection is usually the best approach for mandatory dependencies. And remember, good design is about making our code base easier to change, extend, and test. DI is a major tool in that toolbox. Great way reaching this far. We are building solid engineering muscles. Thank you for your attention. Hello and welcome everyone to day 10 of our low-level design course. Today marks an important milestone. We will move from pure theory into practical, real-world application of LLD concepts. Our focus will be on designing a library management system, a classic case study that captures many core principles of clean, scalable, and maintainable design. Throughout this session, we will apply the tools, techniques, and patterns we have learned so far, culminating in a complete low-level design. Let's dive in and start shaping systems like true designers. Before I start designing, let's first understand the scope and vision of today's project. The library management system we are about to design is intended to manage all day-to-day operations of a typical library. This includes cataloging books, allowing users to borrow and return books, keeping track of overdue items, and maintaining accurate inventory. We will take a requirements first approach, carefully identifying what needs to be built and ensuring that every design decision we make ties back to these functional needs. The emphasis will be on creating a modular, extensible system that can evolve over time without major rewrites. Let's start by framing the high-level requirements. The system must allow users such as students, staff, or guests to search for, borrow, and return books. It must help librarians manage book inventory by adding new books and removing outdated ones. Additionally, the system should track book availability, calculate overdue fines, and generate basic reports like most borrowed books or user borrowing histories. Importantly, it should support multiple copies of the same book, distinguishing between individual book copies rather than just titles. Remember, gathering clear requirements upfront prevents costly rework later in the design phase. Now that we have a clear understanding of the requirements, let's translate them into key components and classes. First, we have the book class, which represent individual books with attributes like title, author, and ISBN. The library class will serve as the central manager, coordinating users, inventory, and transactions. We also need a user class with types like student or staff, each with different borrowing privileges. The loan class will track the borrowing and returning events, capturing dates and statuses. A catalog class will handle book search and lookup operations, while an inventory class will keep track of the available copies. This decomposition ensures that each responsibility is well contained, setting us up for a flexible design. Applying solid principles is the bedrock of building a scalable and maintainable system. Firstly, under the single responsibility principle, each class in our design will handle only one well-defined responsibility. The open-closed principle reminds us to design classes that can be extended, for instance, adding new user types without modifying existing code. Following the least scope substitution principle, subclasses like premium user or guest user should be substitutable wherever a regular user is expected. The interface segregation principle urges us to keep interfaces lean, a searchable interface for catalog, for example, separate from a borrowable interface for users. Finally, the dependency inversion principle means high-level modules like the library class will depend on abstractions, not on concrete classes, making the system more flexible to change. To better visualize our system architecture, we use UML diagrams. First, the class diagram will depict all our classes, their attributes, methods, and relationships like associations and compositions. It will show, for example, how a library has a catalog which manages many books. Next, a sequence diagram illustrates runtime interactions, such as how a user searches for a book, places a hold, and completes a loan. We can also use activity diagrams to map out overflows like book return or fine calculation. These diagrams are powerful tools for communicating our design to stakeholders, teammates, and future maintainers. Once the design is finalized on paper, we bring it to life through code. The book class encapsulates all book related details such as title, author, subject, and availability status. The library class contains methods like borrow book and return book, orchestrating interactions among books, users, and loans. The user class has methods to check availability and track borrowed items. Notice how each class is cohesive, focused, and open for extension, aligning with solid principles. Moreover, dependency injection can be used where appropriate. For instance, injecting a search strategy into the catalog. Through the code, we prioritize clean structure, readability, and modularity. A robust system anticipates and gracefully handles errors. What happens if a user tries to borrow a book that's already checked out or returns a book past the due date? We will design specific exceptions such as book not available exception for borrowing errors and overdue fine exception when calculating fines. Handling these cases elegantly through custom exception classes keeps our code clean and make failure states predictable and manageable. We will also reinforce validation like checking that a user hasn't exceeded their borrowing limit before allowing another loan. Edge cases are not afterthoughts, they are an integral part of a professional design. Maintaining clean, readable code is a non-negotiable standard in professional development. We adhere clear naming conventions. For instance, methods like reserve book are immediately understandable. We use meaningful class names, keep functions small and focused, and write descriptive comments where necessary, explaining the why, not just the what. Refactoring is continuous. As our code evolves, we look for opportunities to remove duplication, improve clarity, and separate concerns. A clean code base isn't just easier to read, it's easier to debug, extend, and scale. At this stage, we consolidate our work. Our library management system design is modular, adheres to solid principles, and anticipates real-world scenarios with proper error handling. The use of UML diagrams clarifies system interactions, while clean code practices ensure long-term maintainability. This design is flexible enough to accommodate future changes, like adding features such as ebook borrowing, reservations, or even a recommendation engine. Remember, a well thought out low level design is the foundation upon which great software is built. That concludes our deep dive into today's test case study. Through this exercise, we have seen how to bridge the gap between abstract principles and real world system design. I encourage you to try building this system yourself, either individually or in small teams, and see what design improvements we can bring. Now let's open the floor for questions. Feel free to ask about any aspect from requirements analysis to solid applications, UML diagrams, or coding best practices. Thank you for your active participation and focus today. You are one step closer to becoming a true system design expert.